So in this video, we'll take some time to talk about problem number 6 from the 2021 AP Calculus BC exam. As question 6 typically is, you're dealing with a problem here that involves an infinite series. And they have an infinite series for g. G has derivatives of all orders for all real numbers. They give us the Maclaurin series for g of x, and g of x the Maclaurin series is going to converge to g of x on the interval of convergence. Now, part A doesn't actually deal with g of x, but it still does deal with infinite series. So state the conditions necessary to use the integral test to determine the convergence of this series, and then use the integral test to show that this converges. Now, to use the integral test, you need to have a function that is related to the rule for the series. So the rule for this series is 1 over e to the n, so my function f of n is simply 1 over e to the n. In order to use the integral test, these conditions have to be met. You have to have a function that's positive, a function that's decreasing, and a function that's continuous. It doesn't actually ask us to show that this function, 1 over e to the n, are these things. It just asks us to state the conditions necessary to determine the interval of the convergence or divergence of this. And we've done just that with that top line. And then if we want to dive into the integral test to show that this converges, we're going to have to check an integral ranging from where the index for the series begins onward to infinity. So this is an improper integral, so to use the fundamental theorem of calculus here, what we're going to have to make sure we do is we get the upper limit of integration to no longer be infinity, and we just pick a holding variable for that upper limit of integration, and then we have to make sure at the end of this we check a limit as that holding variable approaches infinity. So the antiderivative here is negative e to the negative n. I evaluate that at r and 0, which gives me this. Kind of messy with all the negatives there, so just be careful with that. And then if I evaluate this limit as r approaches infinity, you notice this exponent is negative, right? So when I put infinity in place of the r, that e to the infinity is actually going to kick into the denominator, and negative 1 divided by e to the infinity is going to tend towards 0. And then minus the negative obviously can be reestablished as addition. So 0 plus e to the 0, 0 plus 1, is going to give us an integral that converges to 1. And as long as the integral converges, which it does, we know that the series also converges by the integral test. Now, the sum of the series is not necessarily equal to this value, but we have shown that this series does in fact converge by the integral test. Part B asks us to use the limit comparison test with the series that we just showed converges from part A to show that the series g of 1, right? So when we put 1 in place of the x here, the Maclaurin series for g of x becomes what they've written here. Now they want us to show that this converges absolutely. So when you're showing absolute convergence, what you're basically doing is you're checking the absolute value of the rule for the series and not necessarily just the series itself. So if I take the absolute value of this rule for the series, I end up with basically just the opportunity to turn the numerator into a 1. Doesn't matter if we have a 1 or a negative 1 in the numerator, the absolute value of either of those would be positive 1. So this is the series that we're going to be dealing with. Now the limit comparison test requires for us to check a limit as we approach infinity for the series that we are concerned with, which is the one that we're looking at right here, divided by the one that we're comparing with. I think I said that the opposite way I have it written. It honestly does not matter whether or not I have this as the numerator or the other series as the numerator, which is the work that I have shown on my page, and we'll talk about why in just a few seconds. But if I check this limit, I can simplify it a little bit, right? Multiplication by the reciprocal. I do get infinity over infinity. I don't want to claim that this limit equals infinity over infinity, so I just have an arrow, right? This is an indicator that allows us to use L'Hopital's rule. And so when I apply L'Hopital's rule, I check the rate of change of the top, I check the rate of change of the bottom, which then allows me to do this cancellation of these e to the n terms. I get a limit of 2. Now, the numerical value that this limit equals isn't that significant. You need it to be positive and finite to have this test give you a conclusion. If I had this written the other way, like I mentioned a few minutes ago, my limit would have ended up being 1/2. As long as this answer is positive and finite, which 1/2 and 2 both are, I have a conclusion about my series, and the conclusion is whatever the series that I'm comparing with does, and from part A, the series that we're comparing with here, it converges. The one that I'm testing currently is going to do the same thing. So the series that they gave us at the beginning of part B is going to converge absolutely by the limit comparison test, since the series that we are comparing with converges as shown previously. Part C asks us to determine the radius of convergence for the Maclaurin series. So for the radius of convergence, what you're going to need to do is you're going to need to go with a ratio test. So the ratio test is going to require that you take the next term from the series divided by the current term and check the limit of that as n approaches infinity. So when you build your ratio, and I went straight to multiplication by the reciprocal this time around, what you can do is you can ignore any alternating terms, right? The ratio test does have these absolute values here, which allows us to ignore anything that would be causing the series to alternate. So that's why I don't have that transferred into my work here. What I can also do is I can notice that x to the n plus 1, I've got n plus 1 factors of x within this numerator. Well, I've got one fewer factors of x within this denominator. So if I cancel all of these factors of x with all but one of these factors of x, I just have a single x left in the numerator. I'm checking a limit as n approaches infinity. So x is not the variable that's going to infinity within this limit. Therefore, I can treat x like a constant and factor it out in front of the limit. And then what I'm left with within the limit is what you see here. Now, I do have to keep the x in absolute values, right? I don't know if x is negative or positive. I don't need absolute values around this stuff anymore. The stuff that we're left with within the limit is now positive. Now, you do see I've indicated that this is going to give me infinity over infinity. Well, if I apply L'Hopital's rule to that, rate of change at the top, rate of change at the bottom, what I end up with is 2e to the n divided by 2e to the n plus 1. I can cancel the 2's. I can cancel all of these e's with all but one of these e's. And my limit is therefore just going to be 1 over e times what we removed a few minutes ago, which would have been the absolute value of x. Now, the ratio test says that you converge absolutely as long as your limit is less than 1. So if we set this to be less than 1, the conclusion we get is that if x is between negative e and positive e, we are going to converge. Now, notice it doesn't ask for the interval of convergence. It just asks for the radius. Well, this series is a Maclaurin series. It's based at 0. We go up e units from 0 to get here. We go down e units from 0 to get here. The radius of convergence is e. I misread this initially, and when I was working through this, I tried to find the interval of convergence, which got quite messy. You would have to plug negative e and e in place of the x in this series to determine that. Luckily for us, it didn't ask us to do that. So this may or may not be the interval of convergence. I didn't do enough analysis to try to decide if either or both endpoints could be included here. But all we need is the radius, and the radius is e. And then in the last part of this, they tell us that here is the series for g of 1, right? So if you put 1 in place of the x in this Maclaurin series, this is what you're left with. And the first two terms of this series are used to approximate g of 1. We're asked to use the alternating series error bound to determine an upper bound for the error of the approximation. So what I did is I just started applying values of the index, so the index value of 0, 1, and 2. These would be the first two non-zero terms that you see right here. Now, the reason why I went ahead and produced a third term is because if you've ever used the alternating series error bound before, you know that your error bound is established by the magnitude of the first omitted term. So if I'm using these two terms to make my estimate, the most I could have for my error would be the absolute value of this next term. So I've basically said that in writing here. The difference between g of 1 and the estimate from the first two terms, and I've got absolute values there, right? We don't necessarily care if it's an overestimate or an underestimate, but the most possible error that I could have within this would be established by that first omitted term, which would be the term with 2 being placed in for the ends.